Modern AI is doing some truly incredible things. I mean, achieving superhuman results in fields from medicine to finance, it's just unbelievably powerful. But, and this is a big but, there's a massive catch. A lot of the time, we have absolutely no idea how it gets its answers. We get a result, but the process, it's a complete mystery, a total black box.
And that, right there, leads us to this fundamental question that pretty much everyone in the field is grappling with. If we don't understand the why behind an AI's decision, can we really trust it? I mean, should we? Just think about this for a second. Let's put it in a place like a hospital. An AI might be amazing at spotting pneumonia in a chest x-ray, but if it can't show a doctor which part of the image made it think that, how can the doctor double-check its work? How do we know it wasn't just looking at a smudge on the film? The stakes are just way, way too high for blind faith.
Okay, so let's properly define this. Researchers call it the black box problem. You've got these incredible deep neural networks giving us these amazing predictions, but their inner workings are so tangled and complex, they might as well be invisible. And look, this isn't just about whether we feel comfortable with it, it's a real roadblock for science. How can we learn anything new from an AI if we can't understand what it's learned?
So how do we peek inside this box? Well, the old school statistical tests we have, they just weren't built for this. They kind of buckle under the sheer scale and complexity of a modern neural network. And here's the really tricky part. We're not just interested in one little thing, like a single pixel. We want to know if a whole group of pixels, like say the entire upper left part of a lung, is important. And that is a much tougher question to answer.
So to get around this, a team of researchers came up with this brilliant new idea called risk invariance. Instead of trying to untangle the model's brain, they just ask a really practical question. If we hide a bunch of features from the model, does its risk of getting the answer wrong go up? See? If the risk doesn't change, then those features you hid, they probably weren't that important to begin with.
Now, this isn't just some clever workaround. It's actually built on some really solid statistical principles that have been around for decades. As you can see in this diagram, their whole risk invariance idea connects right back to a core concept called conditional independence. The bottom line is, this new method isn't just a cool idea, it's mathematically sound, which means we can have real confidence in its answers.
Okay, so how do you actually measure this change in risk without the model cheating on the test? The idea behind it is so simple, it's beautiful. It's one of the first rules of good science. You never ever use the same data to train your model and then to test it. You need a fresh, unbiased judge.
And that brings us to their solution, the one-split test. It's so clean. Here's the breakdown. First, you just split your data in half. One pile for training the model, and the other pile gets locked away for the test. Once the model is trained, you get to the clever bit. You take that test data and you just hide the features you're curious about. You literally mask them. Then it's just a simple comparison. How much worse did the model do? And that difference gives you a p-value, which tells you, with real statistical confidence, whether that part you hid was actually important or not. So what's the big deal here? Well, this table really nails it. The old ways of testing could really only look at one tiny little feature at a time. But this new one-split test, it's built from the ground up to test a whole collection of features at once. And that ability to look at the big picture is what makes it a real game changer for understanding complex things like images.
Okay, the theory sounds fantastic, right? It's elegant, it's clever, but the million-dollar question is, does this thing actually work when you apply it to messy, real-world problems? Let's take a look at the results. So first up, they tried it on a classic AI test, telling handwritten numbers apart. They asked the model if the upper loop of a number was important for telling a 7 from a 9. And the result? A p-value of pretty much 0. It's statistical proof of something we all know just by looking at it. Yep, that little loop is absolutely crucial. Now let's go back to that high-stakes example, the pneumonia x-rays. They tested a region over the left lung, and the test came back with a p-value of 0.026. That is statistically significant. It's solid evidence that the AI is in fact looking in the right place to make its diagnosis. This is a massive step forward for building real trust in medical AI.
And get this, the method isn't just for images. The researchers showed it works all over the place. In drug discovery, it correctly pointed out what was important for a drug's effect. For facial recognition, it confirmed that an AI uses the eyes and mouth to read emotion, and hey, not so much the nose. And for movie reviews, it proved that the AI was actually paying attention to the right keywords. The versatility here is just wild.
You know, the authors themselves really said it best. They've built a practical tool that lets us finally look inside these black boxes. And the key thing is that it works on the messy, complex data we actually care about. And it does it without all the restrictive assumptions that held back the older methods.
So let's just quickly recap everything we've covered. We started with this huge black box problem, holding back both trust and science. Then we saw how this new idea, risk invariance, gives us a smarter way to ask if a feature really matters. We learned how the one-split test uses a simple trick to give us a fair, honest answer. And all of that together gives us this powerful new tool to finally start understanding what these incredibly complex AIs are actually doing.
And all of this leads to one final, really powerful thought. For so long, the incredible promise of AI has been shadowed by this fear of not being able to understand it. But with tools like this, we're finally starting to pry that black box open. And as we get better and better at actually proving what an AI is thinking, the question changes. It's no longer if we can trust it, but what are the next big, important, maybe even life-changing decisions we'll be willing to trust it with?